Welcome to the Computational Fabrication Seminar.
A web series showcasing new research, exciting ideas, and exchanging thoughts.
Our weekly 1-hour live sessions rotate through 3 different time zones and are jointly organized by IST Austria, University of Washington, and Singapore University of Technology and Design.
Each session starts with a motivational opening talk given by an expert from industry or a field related to computational fabrication, such as robotics, computer graphics, mechanical engineering, material science, HCI, applied math, design, or architecture.
The motivational talk is followed by a technical deep dive. We invite our audience to ask questions during the talks via YouTube comments and join us afterwards on Discord.
Good afternoon. My name is Michal Pivaci, and I will be the host for today. The theme of this week is Fabricating interfaces. It is my great pleasure to introduce our motivational speaker for today, Jennifer Mankoff. Jennifer is the Richard L. Adler Professor in the Paul G. Allen School of Computer Science and Engineering at the University of Washington. Her research is focused on giving people the voice, tools, and agency to advocate for themselves. She strives to bring both structural and personal perspectives to her work. For example, her recent work in the intersection of mental health and discrimination uses sensor data to explore how external risks and pressures interact with people's responses to challenging moments. Similarly, her work in fabrication of accessible technologies considers not only innovative tools that can enable individual makers, but also the larger clinical and sociological challenges to disseminating and sharing designs. Jennifer received her PhD at Georgia Tech, advised by Gregory Abbott and Scott Hudson, and her bachelor from Otterly College. And today her talk will be about massings on creation, by whom, how, and what we create. And Jennifer, the floor is yours.
Thank you. Just making sure I have the screen share set up properly. Thank you for having me. Should I turn my video on now?
Yes, please.
Okay, how's this? Great. So thank you for having me today. I'm going to try to provide some new and different perspectives, hopefully on fabrication that have inspired some of the work that my group does, the technical work that we do, as well as some of the qualitative work that we do. Just some thinking around what is creation about and why do we do it? And I wanted to start by thinking about craft in particular and what craft is, because for me, that's where my interest in fabrication came from. And this is a picture of my daughter, who's now 15, when she was about 2. And she's wearing a pair of knitted gloves and a knitted hat that I made for her. And I want to highlight some things about this. You know, she's posing for the camera. She's really excited. The mittens are obviously way too big for her, which, you know, happens. But for me, knitting for her was a way of giving her kind of a hug that she could wear around even when I wasn't there to hug her, and showing my love for her. It's also something that's practical, that is comfortable, and that fits real needs. And that's a big motivation for a lot of people who make those kinds of things. Of course, making and craft happens for many different reasons. And so here I have an illustration of 2 breasts that are made, they've been crocheted. And these are part of a project called Knitted Knockers, which is has people volunteering all over to produce these breasts for people who have had to have a breast removed for something like breast cancer. In addition to fitting a real need and being comfortable, often being an expression of love and being very practical, this also represents craft as a form of healing and empowerment. And these are considered much more comfortable than many of the alternatives. Here's another version of something that I would call empowering. So what you see here are 2 robots that were crocheted by a knitter for a child with a disability. And one of them has a limb difference. It has a shorter, smaller arm. The other one has a prosthetic leg, and both of them have big hearts on their chests. And then here again is another example. And what we see here is a pair of fashionable pants. This is actually 2 advertisements. These pants were made by the same firm. So this is a form of craft as professional entrepreneurship. I also chose these images because they represent an interesting aspect of the space of how we conceive of craft. The one on the right, which shows a woman in a power wheelchair wearing pants that are stylish but modified slightly to fit the needs of a wheelchair user, was rejected by Facebook's automatic ad service, which did not recognize them as the sort of standard thing that was considered acceptable for advertisements. And this had a huge impact on, and there's several examples of this in the article referenced below, and the business's ability to succeed, because the process of getting those rejections overridden is quite onerous and affects advertising revenue and visibility of a product. So I will then turn to one last aspect of craft that I think relates to that image as well, which is the idea that craft can be subversive. And what you see here are two images that represent this. One is a hand-embroidered television screen with a picture of a woman who is bare-chested facing a mirror, and on the mirror her breasts are covered with the word censored, and it says new mirror by Facebook, patriarchy approved. So this is very much a subversive, expressive artifact. On the top left of the image, you see a garment by a German seamstress dating back to the 1890s. She had been consigned to an asylum, and although this garment is often falsely described as her straitjacket, it was actually cut and assembled from a hospital gown, tailored, and then turned into her autobiography. So the writing is embroidered on it as the story of her life and her experiences. And I should say that asylum placement in asylum in that era was often a form of control and not necessarily a form of healing. So craft is something that is thousands of years old. It has many values and uses, and it is also something that's highly skilled. And I just want to illustrate that with this image from Daniela Rosner's book, Critical Fabulations, of memory that was produced by women who had experience working with fibers for NASA. This was a very old and original memory chip on a computer. They were referred to colloquially as LOLs, or little old ladies, because that was the group of people that had the expertise to do this carefully refined work and do it right. And here's another example of craft again from the Spanish flu. This is a mask that was made by one of many masks that were made by many army nurses who were working at the time to try to help create face masks to keep people safe. So craft is something that is highly skilled. It's thousands of years old. It really was only labeled arts and crafts after the Industrial Revolution. Prior to that, it was just part of what people did to make the things that they needed. And since then, it has become often centered in women's busy work, and sometimes denigrated because of that in comparison, for example, to art with a capital A. It is also exceptional at addressing unique and individual needs because of the level of control that makers have over their craft. And so here I just show some examples of books that have been published about do-it-yourself accessible technologies for people with disabilities, as well as a Thingiverse page that shows a variety of objects that were created by Thingiverse users, including a wheelchair ramp for a door, a card holder, and a tangible book, like I think there's an example of Dear Zoo here. So craft is happening now. Lots of people are doing it, and users and many others, and it's got many varieties out there in terms of the materials that are used, what it's being used for. And I would also say who crafts. And so I just want to start in beginning to talk about how might we expand who crafts and who we think of as crafters. So as an example, my student Taylor Gottfried presented a paper at CHI this year on her interviews of crafters with disabilities. So we interviewed 16 disabled knitters, including 11 who were blind or low vision, 7 with motor impairments, 3 with cognitive impairments, and many of these also had fatigue or arthritis or other things that also affected their crafting experience. We also looked at 6 forums to expand our sample size. And what we found was that even though there was an active participation in this kind of craft by people with disabilities, the people who were designing patterns didn't necessarily consider that. And so forum posters, for example, mentioned over 40 different pattern formatting guidelines that could make patterns more accessible, but pattern accessibility was a frequent problem for the knitters we interviewed. And not just PDF accessibility to screen readers, but also how patterns were designed and for whom. For example, one participant with motor and cognitive impairment said that if it says you need to go and knit 16 rows, I'll write out all of them and then I'll mark them off as I go. Yet the way that patterns are produced today doesn't have the flexibility to recompile them into new formats or reformat them automatically. Something that could easily be automated if pattern languages were structured enough. And they're close to that. We've built compilers that can actually take standard knitting patterns and turn them into knittable, machine knittable representations that could be printed therefore in machine code or as a hand knit pattern. So it's not a big leap from there to think about reformatting patterns based on individual need. 4 participants reported difficulty with the tools they used for their craft. For example, one said, when I purl, I have to push my thumb down like that to get tension. And so there's a lot more pinching for me, and that definitely causes discomfort fastest. And so the size of stitches people knitted and the tools they used to knit with, as well as the particular kind of stitch, were all spaces that they might need to modify a pattern to make it more accessible. Again, I'll suggest that if we could parse patterns and reproduce them in varied ways that address these kinds of needs, that would be an interesting tool opportunity. Finally, I will mention that patterns, the output of patterns, the things that were created were modified sometimes to address accessibility issues. For example, one wheelchair user told us, if your sweater is too long in the back at all and it goes underneath you, it makes it hard to transfer out of your wheelchair. And so instead, the goal would be to have a shorter back and a longer front. And the toy robots I mentioned earlier are another example of a modification to a standard design to meet an accessibility need. Lastly, I just want to mention that participants did mention that they encountered ableism among other knitters that they interacted with. For example, one reported a pattern designer who didn't like the idea of a wheelchair being in a shot of their garment. So these kinds of assumptions are obviously not unique to the knitting community, but just a reminder that as we think about who crafts, we might want to think about how open they are in the spaces in which they do craft. So crafters with disabilities is one example of how we might expand who crafts and where tools could play a role. Another space that I want to highlight is domain experts. So this is a space that we've been working in now for several years, and we've done a whole series of different case studies. This is with a variety of different collaborators of mine in a variety of different settings, including clinical settings, volunteer settings, in sports groups, both within and outside of the US, and of a variety of lengths. So I'm not going to go into depth about any of these papers because there's too many of them to cover in the time that we have today. But I do believe strongly that part of how we learn what kinds of tools are needed is to try to understand what the communities who are doing craft and making already are, what kinds of barriers they're running into. And I just want to highlight a couple of those today. So one of them is that there can be conflicts between community values and clinical values in the case of medical making. And so there's, for example, a very strong belief and a lot of good reasons to involve clinical expertise in making, but the value of sort of doing the right thing and doing it really well conflicts sometimes with community values, such as help where you can. So do whatever you can to help, even if it's not perfect. And we saw a really stark instance of this in the work that Megan Hoffman and Udaya Lakshmi, we saw a really strong instance of this that was presented at CHI this year, where there were angry communities who were really upset at being asked about safety during COVID, when they thought that the most important thing was to get PPE to people regardless of how good it was. And the level of anger there was particularly striking as an example of how hard it was for some of the DIY communities to accept the constraints that the medical community wanted to impose, even though they were producing devices for the medical community. And then, looking at it from the other side, we've seen examples of things that really are like joyful and helpful, but may not fit a certain clinical pattern that may be hard to get acceptance for or support for in the medical side of things. Both communities believe in the value of longitudinal support, and I would say to varying degrees, both struggle at times with providing it. Okay, so the last thing I wanted to sort of say on this topic was that I think there's opportunities here to think about differently about what the goals are for tools. So for example, we could share skills instead of designs for safety reasons, and that might still be of value to the DIY communities without triggering concerns in the medical community. Another thing that we saw in some of this work was that small adaptations were better than large iterations within client. And so the idea of what iteration means being different depending on whether you're working with an individual who has a specific need versus across clients is an interesting one to consider. And then the need to support durability over time, not just of the relationship with the client, but also the specific thing being printed or produced is an important one to consider, because durability isn't necessarily something that we typically test in iterative design. And when we're fabricating, it's really can be important. And then finally, thinking about supporting cross-client reuse of patterns, meaning how do we design patterns that can be modified and reused easily, is another opportunity, I think, for tool development. So I'm just going to touch on a couple of brief examples of this. Oh, I think I've gone over, haven't I? How are we doing on time?
Perfectly fine.
I'm just doing a time check. Do I need to finish up, or are we still okay?
Still okay.
Okay. So one of the things we want to think about is expanding who can use automated tools as part of their craft process. And what I think is important to realize here is that from an end user's perspective, the things that we take for granted in end user programming and software engineering are simply not available in the off-the-shelf commercial tools that support making today. And so if we could develop better support for production and personalization of both interactive and static objects, I think we would see a large an increase in the set of patterns that are being innovated and shared, even beyond what we're already seeing on sites like Thingiverse. And the first thing I want to highlight that is missing from what many tools support is modularity. So how do we do modularity? We could imagine thinking about being able to reuse kind of functions like a bounding box or a mold or a swept path function, and using them in multiple contexts and having them self-identify whether they're being used correctly, being able to add to patterns, error checking support, and doing it all in a way that is easily accessible to end users. And when we did this in the parts project, which Megan Hoffman, who is, by the way, going on the job market next year, that was one of her early contributions to the tools literature. We found in a workshop that the ability of end users to achieve viable product and to get through all of the steps between an initial design concept and that product was much, much higher when they had access to these kinds of reusable functions than when they were using the raw tool without that support. So that's one important aspect of what we want to do. Another thing that I think we need to move forward on is requirements specification. And so, for example, if we look at this lampshade, I might want to develop a knitted pattern that will curl and cling to the frame or let light through. And as an end user, I want to specify my requirements in those higher level terms. The question then becomes, how do we specify those? How do we support a structured form of specification and control, and then tie that into an automated system? And so we've been working on optimization-based solution finding for this, where both tactics and objectives can be specified by the end user. And then the algorithmic side of this is just a tool-based thing that is pluggable using these kinds of tactics and objectives. And we've also been exploring what aspects of the algorithmic side of this need to be under the control of engineers versus being built into the tool and solely controlled by end users to make this possible. So there's some subtleties here, but I think there's a lot of opportunity in thinking about how we let people express a really wide variety of objectives that meet their conception of craft as opposed to what's easy to do computationally. And we've applied this approach to everything from knitting, as just shown, to tactile maps. The last thing I want to mention is thinking about how we can support hybrid control and sort of just going further down the line of selecting algorithms that encapsulate people's own way of thinking about design. And so here I want to highlight a paper that Ben Jones and Adriana Schultz led that I was part of on computational design of knit templates. And the key insight here was that a quad meshing algorithm had properties that mapped onto the way knitters think about pattern design. They mapped onto the way you make decisions about where to put seams or change direction in your knitting and other things like that. And so that then allowed hybrid control, because by making modifications to the inputs to the quad meshing algorithm and modifications to the way quads were read by the pattern generation program, knitters were then able to generate hand knittable or machine knittable patterns that were sort of beautiful from a pattern designer's perspective. So to close, I want to just remind you that this was just a brief tour of some of the things that we really ought to focus on, and just there are many, many more open challenges, from quality control to how we increase support for rapid prototyping and for testing out designs without having to fully manufacture them, to how we support clinically relevant changes to patterns and or staying within clinical parameters when we modify patterns, to how we manage longitudinal viability over time. There's just a lot of open questions. And so that's where I'll leave you, is with hopefully food for thought. Thank you.
Thank you very much for your inspiring talk. And I would like to remind the audience to post their questions in the chat for the joint question and answers at the end of the session. And today, our deep dive speaker is Michael Wessely. Michael is a postdoctoral researcher in Professor Stephanie Miller's HCI Engineering Group at the Computer Science and Artificial Intelligence Lab at MIT. He received his PhD from INEA Paris-Saclay, advised by Professor Wendy Mackay and Professor Theopanis Tsandilas. His research focuses on the fabrication of physical user interfaces using smart materials at the intersection of HCI, computer science, material science, and engineering. He has published several papers at ACM High and ACM West, the leading conferences in human-computer interaction, and received for his work 2 Best Paper Awards and a Best Paper nomination. Michael will give us a deeper view on fabricating physical user interfaces. And Michael, the floor is yours.
Yeah, hello everyone. Thank you very much, Michael, for this really nice introduction, and I'm really excited to be here. So let me first share my screen on the presentation. Right. Yeah, technology is always hard. So can you see my screen?
Yes.
Okay, super awesome. So yeah, hello and welcome everyone on this talk. Today I will talk a little bit about fabricating physical user interfaces. So, and at first, let us talk a little bit about what are these physical user interfaces, and do they actually have any relevance in our lives, right? So if we look at a few of examples of physical user interfaces, we see, yes, they have an extremely high relevance for our lives. They kind of influence how we live and how we work. One of these examples, for example, in transportation, when you look at all these modern cars, especially the electric cars, they have a touch screen that allows you to control the temperature, select a specific music. Same for communication, of course. Everyone has a smartphone in their pocket to interact with the digital world using apps. Also on smartphones, you can have usually also an app on the phone that lets you control the light, the color and the brightness in your room. And also for health, it is very relevant. So these health trackers become more and more popular. And that they even influence how we feel, and maybe even how old we get and how fit we are, right? So what have most of these physical user interfaces that we use nowadays in common? This is that most of them have very similar form factors, right? So most of them are some kind of touch screens. They are rectangular, they are rigid, and that's what is our utility that we have in interacting with the digital world. So, and my research interest over the last couple of years was the question: is it also possible to just make our entire world interactive? Can we make everything interactive? And with this, I mean, is it possible to seamlessly integrate ways to sense users, like sensors, and also to give output to a user, for example, with integrated displays that conform to any kind of geometry, may it be flat or curved, that is scalable and can have like any kind of size from very small to very large, and can integrate into a large variety of different materials, right? Just to like go away from this metaphor that everything has to be rectangular, rigid, and has to be a touchscreen. So, and to illustrate how I imagine this future to look like, I want to show you directly like one example of one of my research projects. And here, please focus on the sofa. And this sofa is fully interactive. And as you can see nothing. So these sensors that we integrated here are made with a transparent ink that is not visible. It perfectly conforms to the material used here. So this is leather. This is challenging. Has a lot of wrinkles. It is soft. It can bend. So, and here, one of my students, Jackson, will demonstrate how this user interface works. So once he sits down, the system can recognize this, then starts this photo album on the screen right here. And we have a swipe sensor on the armrest. And while you are moving with your hand over to the left and to the right, you can navigate through all the different images. And once Jackson is happy with it and has seen what he wanted to see, he gets up, the system recognizes this again and can turn off this, this photo app. So like achieving like this kind of integration for physical user interfaces is, of course, something that that isn't solvable with just working in one research area, right? This is a very interdisciplinary field, and like one of the areas that have to be advanced as fabrication technologies on the one hand, but of course we also need smart materials that can fulfill specific functions. Let this be conductive materials for sensors, but also color changing or shape changing materials. Another element that we need here are computational tools on the one hand on the design side, so tools that support makers in fabricating these more and more complex physical user interfaces, but also for capturing the data and processing what we get from these physical user interfaces in a meaningful way. And third, of course, engineering, because in the end, when you build these things, everything has to be connected in the correct way, such that we have a functional user interface in the end. So, and over the last couple of years, I worked a lot on like all of these areas. And when we look where I would locate my work, there's not one project that was just focusing on one of these research areas, but it was always an interdisciplinary thing with at least like 2 of these areas touched, and sometimes even all 4 of them, which were, of course, like the most challenging projects, but also, in my opinion, the most rewarding projects. So, all right. So since this is a quite challenging question, in this talk today, I want to show you 3 different angles how I approach this challenge, and illustrate this with 3 different projects that I did over the last couple of years. So, and the first angle that I took was the question, is it possible to reprogram the appearance of objects in the physical world just as easy as you can just like change the appearance of an object in a digital world with a 3D model, for example? The second angle that I'm interested in is how can we seamlessly embed sensors for capturing user input and displays for outputting communication to the user in user interfaces that can take any scale, any size, and also conforms to various kinds of materials. And the third direction I was interested in is the question, can we even like sense and potentially even manipulate material properties themselves of the physical objects that surround us? So, right, and with this being said, I want to get started. So we go from left to right. So we'll start with the question, how can we actually reprogram the appearance of objects? So, and this is again something very challenging, but on the other hand, in the digital world, this is something very easy. So if you look on the left-hand side on this digital model, if you would like to recolor this digital model, for example, in Blender, you would just click on diffuse color, select a new color, and this entire car model would have a different color. So this is very easy. So like changing color is not a challenge in the digital world. However, if you look at the picture on the right-hand side, it is a big challenge to do this in the real world. So if you have a car and you want to change the color, you have to bring it to a paint shop. You have to pretty much give these people like all the money that you have, wait for a long time, and then they can recolor it. And this is certainly something that you cannot do every day and all the time. If you want to like personalize your items, like your car, for example. So changing color in the real world is hard. And the project that we did here was about like can we make this easier? So, and what we came up with is a smart material that uses photochromic inks. The smart material is just is a paint that you can spray on the surface of various objects, just like we do it here. We use here an airbrush. And then we use light, so ultraviolet and visible light with actually just a regular office projector to reprogram this smart material to change its color and to change the appearance and the surface texture of physical objects. So you can see here we have applied a colorful checkerboard pattern on it. And this process is also reversible and reprogrammable. So we can erase the pattern and then replace it with a completely different pattern, like this black and white zebra pattern right here. We can, so since this is just a spray paint, we can apply it on any kind of object. So we also sprayed it here on a phone case, something which you take with you like all the time. And here I put like an image of my Tokyo holiday on it, just to like to personalize, and it reprogrammed the phone case to make it mine, right? So we were also very much interested into like integrating it into textiles, into things that we can wear to personalize them. Here we like sprayed it on a shoe and then reprogrammed it. So, and of course, like it's also exciting to be able to reprogram your car. So like imagine a scenario where there's like a car sharing service and each customer who takes the car just for the next hour, for the next 2 hours or so, can reprogram the appearance of this car, put an identifier on it to know that the right customer has the car and personalize it to their preferred designs. So here I want to show you again, like how these examples look like after they are reprogrammed. So yeah, you can reprogram it like with 3 different designs. The transfer speed is between 20 to 40 minutes, which depends a lot on what kind of colors are used for reprogramming these phone cases. So here we have a collaboration with a company, New Balance, that focuses a lot on textiles and on wearables. And we are working there at the moment to extend this project also to other wearables. And then we illustrated here this example with a car because we also collaborate with Ford, and we want to see like in the car industry and in transportation, like how can these photochromic reprogrammable textures be useful. At an upcoming collaboration that we will soon, or like we already started with it, is the question, how can we maybe reprogram textiles themselves, so with integrated smart materials and control over it without any external light sources needed, but making these textiles reprogram themselves. All right, so this sounds, of course, like if you don't know the project, it sounds a bit like magic. So is this actually working somehow in a reliable and reproducible way? And yes, it does. So these photochromic dyes have this property that they're normally in the transparent state. But if we shine UV light on it, like we do it right here, they can be saturated and take different kinds of colors. And this process is also reversible. So if we shine visible light, so white light, for example, on it, if you look carefully at these liquids, you see that they desaturate again and then reverse back into this transparent state that they had initially. So this process is repeatable, right? So we can see this here. So we have a nice control using specific wavelengths of light, right? So you have UV light for saturation and visible light for desaturation to control the saturation of these materials. But the problem here, and this is in contrast to the example that you've seen before, each one of these photochromic materials, of course, has just one color. So it can only like change from transparent to this particular color, but you do not have a large color space. And the question is, can we make this happen? So, and our idea to realize this is inspired from the inkjet, from printing technology. So like inkjet printers, you might know, have these like cyan, magenta, and yellow cartridges. And by mixing these 3 base colors together, you can achieve a large color space. So, and we took this idea and transferred it also to photochromic dyes and selected 3 photochromic dyes, cyan, magenta, and yellow, and just mixed it all together into one ink. And you can see like when you mix it together at full saturation, it becomes black, just like it should do. So, and then we did some experiments and tried to desaturate the individual channels of this mixture. So trying, for example, to desaturate just cyan, such that only magenta and yellow are fully saturated. And then what comes out is red, for example. And we tried this with different colors. And you see on the right-hand side of the slide, like a bunch of bottles, and they're all the same bottles and the same liquid. So we didn't change it. We just reprogrammed it by carefully changing the saturation of each one of these photochromic dyes that is in this mixture. So now the question is, of course, how can we control the saturation of each dye? So for this one, let's look at the absorption spectra for each one of these dyes. So absorption spectra in this case means what kind of light interacts strongly with this photochromic material and makes it and induces actually this state change from a transparent to a saturated state. And we see that they have very distinct and particular spectra where they are extremely active or not active. So like let's look at yellow, for example. We see that yellow has a peak at around 400, let's say 40 nanometers, where it absorbs a lot of light and then it changes its saturation like quickly, while in other ranges of the light spectrum at 580, so other colors in the visible spectrum, it's actually not affected at all by it, right? And the same is true for magenta and for cyan. So and now our idea is, if we want to control the desaturation of these photochromic dyes, we have to shine light on it in a very specific spectrum that overlaps with the peaks of these 3 photochromic dyes. So and we started doing this with actually just a regular DLP projector. And the beauty about this DLP projector, or like any projector actually, is it has 3 different light sources. It has like a red LED, a green LED, and a blue LED. And if we now overlay the spectra of these 3 LEDs over the absorption spectra of the photochromic dyes, then we see that we actually have a quite decent overlap here. In that sense, for example, let's look at the red LED on the right-hand side, so this red dotted line. So this red dotted line has a very strong overlap with the cyan photochromic dye, right? So this means that like red light will strongly influence and speed up the desaturation of cyan. However, it has just like a very small overlap with magenta, so it might have a little influence on magenta, but not that much, and has absolutely no overlap with the yellow photochromic dye, which indicates that red light will most likely not affect yellow photochromic dye and its saturation at all. So, and this is exactly what we did in these projections. So when we look at the phone case again, like these projections are just combinations of red, green, and blue light per pixel. And each one of these pixels just gets a specific amount of light assigned to it for a specific amount of time, right? And this is how we can create these high-resolution multicolor textures. All right, so let's look a little bit if like how we can actually come to know for how long we have to shine red, green, and blue light on this photochromic dye, and we actually had to develop an algorithm for it. So, and the reason for this is that like we so the goal here is to understand exactly what the impact or the result is of shining a specific light source like red or green or blue light on each one of these dyes, and like see how long does it actually take to like desaturate these photochromic dyes. So, and for this we conducted an experiment. So what we did here was we sprayed cyan, magenta, and yellow dye individually on a test cube. All right. In order to study the impact of different light sources on each one of these dyes individually and to better understand it. So, and then we measured visually how the saturation changes if you shine light for a specific amount of time. So like for specific samples of time on it. And we can see here one deactivation graph that we made for the red light. We did this also for green and for blue light, of course, but let's focus here on the red light for simplicity. So, and what do we see here? So if we shine red line, so on the x-axis we have the illumination time, and on the y-axis we have the relative saturation. So how much of the color is like still there after shining red light on it. And the assumption here is that we have one light source that can control exactly one of the photochromic dyes, ideally, and doesn't affect the others. And this is partially true in this case. So we see that red light does not influence the saturation of yellow at all. So it pretty much like stays at 100% with a bit of fluctuation. The second assumption is that red hopefully deactivates cyan very efficiently, so we can take it out and reduce the saturation here efficiently. And this is also true, so it has a large effect on cyan. Unfortunately for magenta, we also like have it is a slower desaturation as for cyan, but still it desaturates over time. So let's look at the graph again of the absorption spectra and the wavelength why this is actually the case. So red light is, again, the red dotted light on the right-hand side, and we see like a large overlap with the cyan photochromic dye. So of course it deactivates it fast, but we also have a tiny overlap with the magenta photochromic dye here, and this is actually inducing the reason for this slower desaturation of magenta. However, if you look at the absorption spectra of yellow, then we see that like the spectras of yellow at the spectrum of the red LED is like so far away that there shouldn't be any influence. And we see this actually in our experiment that yellow is not influenced by it. So you see already, this is now like a quite, it is not that easy to actually like define like for which kind of amount of time we have to shine a specific light on it to achieve like a specific like a target color, since like all of these like dyes are somehow influenced by it. So we had to like create some computational model for this. So and the premise that we have to solve here is that if we start from a specific color A, so this is a sample that is like fully saturated at 100%, how do we actually get to a specific target color B that we define? So any arbitrary color B. So and the goal of this is that we in the end come up with a set of seconds, like a set of timings for the red, for the green, and for the blue light, where we hope that if we have color sample A and we shine, for example, 200 seconds of red light on it, 380 seconds of green light on it, and 20 seconds of blue light on it, that we end up in the target color B that we actually wanted to have. So how do we get to this? And for this, we formulated an optimization question. So like a minimization. So the minimization term here is a simple sum, and it consists on out of the target color that we actually want to achieve, and an estimated color that depends on the illumination time t. So t is here like a three-dimensional vector with the time for like red, green, and blue light in seconds. All right. So and if these two if these two values become equal, so if you find a specific t such that ct equals b, then this term will be minimal, and that's the goal here. So we minimize for t to like make this term as small as possible, right? So but we need, of course, like some function that estimates the color c given a specific illumination time t, and to come up with this, we formulated this term right here. And this looks a little bit scary at the beginning because they're so long, but it's actually quite easy to understand. So so we start on the left-hand side and then move over to the right-hand side. So we always like start with color A, so to say. And color A is always the CMY formulation, our coating at 100% saturation, and all three color channels, cyan, magenta, and yellow. Okay. So and then the first term that we have here, this A times TR, is the impact of red light on this particular on a fully saturated sample. Okay, so this means like if we shine for a specific amount of time, TR, let's say 200 seconds, on this like fully saturated sample, it will have an impact on the cyan, magenta, and yellow channel, and we have this impact through our evaluation where we check like what actually happens to all of these three dyes if we shine, for example, red light on it. So, and then we just go on with this. So like we include the impact of red light on the fully saturated sample and subtract it from it. And then we do the same for green light and subtract it from the fully saturated sample, and the impact of blue light from the fully saturated sample. And then what you end up is the sum of like all the impacts combined of red, green, and blue light. And this is then our final target color. And this is then the term that we can use in our optimization. So, and then now the question is like, how can we actually mix this photochromic spray paint? So, and for this, you just need a bunch of tools. So we use as a base the like a car lacquer, pretty much. It's not expensive, like 1 liter for $15 or so, $20 maybe. Then a beaker, a mixer, and then these photochromic dyes. They are commercially available. You can find details in our paper. They come from a company called Yamada in Japan, and you can just like buy them. So, and the procedure here is that you put the lacquer into a beaker, and you add a specific amount of photochromic dye. Again, details on how much exactly is something that you can find in the paper. And we repeat this process for the other photochromic dyes, magenta and yellow. All right. So, and once everything is nicely mixed together, we can put it in a vial. And now here you can see, like if you shine UV light on it, it directly changes its color and it becomes more saturated. So, and then the final step is, as we described it in one of the previous slides, like we just mix all of these three base colors together, and then what it ends up is this kind of dark color, this black that you see like here in the speaker. So then the final step is then to just like spray it on the surface of materials, and this object is ready to be reprogrammed. So now's the question, after we did this and submitted the paper and everyone was happy, like what are actually the next steps here? So one of the limitations that we have at the moment is the limited amount of colors that are commercially available, right? So ideally, if you have these base colors, we want to have a cyan that is like a photochromic dye that is like as close to like a real cyan as possible, and the magenta that is as close to the real magenta as possible. Unfortunately, this is not really the case. So we use the 001 blue material here for cyan. This is close enough to cyan for our purposes, but of course not perfectly cyan, which limits our color gamut that we can achieve. However, there's also some hope at the end of the horizon. So new photochromic dyes are getting developed, and we got in contact with our supplier, and there are a few experimental colors that are closer to the cyan that we actually need. And we are like, at the moment working on incorporating these into our system. Then another exciting direction that we go into is 3D printing. So if you're familiar with like SLA printing and DLP printing, where you have a resin that you can cure with UV light, then you know that multicolor resin prints are at the moment not really possible. Always because you have just like one resin tank, right? And you have to print your object with this one resin that you have in this tank, so you cannot really do like multicolor, right? So and our idea here is that we mix photochromic materials into the resin, and we had already some successful experiments with it, and then we use an additional DLP projector to selectively desaturate the photochromic dyes like in this resin while it is being printed, and then hopefully achieving like a multicolor resin printer in the future. So, and transfer speed is, of course, like another question. So at the moment, like reprogramming these materials takes something like 20 to 40 minutes. And we are looking into possibilities to accelerate this process. And one idea is, of course, to just like increase the intensity of the light. We tried this, and this worked like well, like double the power means like half the saturation time, which is like super awesome. But I'm pretty sure like at some point, this photochromic material will just burn off and be completely like annihilated. What we did, like, so we were also like looking into other methods to like accelerate this process. So, and like just recently at Kai a few weeks ago, we presented a paper called Chromo Update that takes like a different approach to reprogramming photochromic materials. And instead of like using a UV LED, this is like this is what you see right here. This is this light source that we use to activate and saturate the materials. We use now a UV projector, and this has a very important implication. And this implication is that the UV projector is like a full HD projector, which means we have pixel-wise control over the saturation. And with the RGB projector, also pixel-wise control over the desaturation process. And this enables us to fine-tune the entire reprogramming process. You can see here our entire setup. We have these two light sources, these two projectors, and then you just place your object in front of, like on top of this turntable, and you can reprogram it. So what we achieved with this are grayscale previews that only take 60 seconds to reprogram the surface texture of a material. And the second is our texture-to-texture updates that are faster than the method that I presented before. So let's take a quick look at how these like grayscale previews work. So and the idea here is that we just use the UV projector because the saturation of the material is extremely fast. We can apply a grayscale texture in just 60 seconds on the surface of this material, and then just take it out and we can use it, which is extremely suitable for like fast design iterations if you, for example, just want to try something out, right? So another element that we implemented here are direct texture-to-texture updates. And the idea here is that you have, for example, a notification mark, and you want to update it on a daily basis, maybe like even every hour, to reflect like new information. For example, if you have like a weather app here and like a set of your meetings, it would be great to just like being able to like update it like all the time and have your schedule every time with you when you're drinking coffee. So and that's what we did here. So we go here from the left texture to the right texture, like 2 times passed, 2 meetings are done, the weather changed a little bit, and you can just simply update this notification mark to reflect the current state. So All right, so far about the first angle on this, like reprogramming the appearance of objects. And next, I want to talk about advances that we had in embedding interface elements, so like sensors and displays, into objects of any kind of scale and any kind of material. So yeah, the big challenge here was we have a vast and exciting physical environment, but how can we actually embed sensors into everything? And the method that we use here is spraying. So what we do here is we have here a conductive material. It's a copper spray that we can apply on surfaces with a spray gun. All right, and so once we spray these conductive elements, we can also add designs to it and personalize it and make it beautiful. So, and this is then like an interface that you can build that actually covers the entire wall of a house. So we have like here like an electroluminescent touch display. Once you press it, you can turn on the light. We implemented here 2 sliders that enable to change the brightness of the lamp that you have, and another slider with which you can control the color of your home. So like what did we use here? So like what you just seen in this example is this copper ink, and this copper ink has a pretty high conductivity, and it's really suitable for like spraying touch and proximity sensors. You can also implement sliders. You need to connect everything, of course. So you need wires and a connection to a power supply and a controller that can capture the signals and process them. However, except like instead of this copper, which is of course very visible, we were also excited about like seamlessly integrating these user interfaces with a material that is transparent and is not directly visible and doesn't change the surface texture of materials. And it turns out that there is a material called P.PSS. This is a clear conductive material that can also be sprayed. And here you can see like how we did this. At first, like you see, pay attention to these lines over here. These are projections. So we have a projector in front of the sofa, and we implemented a user interface where you can design these sensors and traces digitally, and then use a projector to produce guidelines that help you fabricate these sensors and elements for your user interface. And then all you have to do is like using P.PSS, put it into your airbrush, and you can spray it on the surface of the sofa. So in the initial example that you've seen, we will also see it again. This is the material that we used for integrating the sensors. They are almost invisible, but conductive, as you can see it right here, and they can be used for sensing. So yeah, and this is this example that I showed you already in the beginning. And here you can see like where we like place these sensors to capture Jackson when he sits down and starts the photo album. So here you can see this user interface that we developed. So given that you have a 3D model that you, for example, can scan with your mobile phone or so, we have a set of tools implemented that lets you add interactive elements, that lets you add the connectors to microcontrollers and draw the wires. And then this can be then projected on the object with a projector system, or you can also export it as a PDF to produce stencils. All right, so apart from conductive materials, there are also other materials that you can spray, and we also looked into this. So there is, for example, dielectric material for insulation. There is phosphor that can even light up. We use this in this lamp example, in this electroluminescent touch display example. And while this like explaining exactly how this works is maybe too much for today, but like you have to spray then several layers on top of each other with phosphor, clear conductor, copper, and an insulator. So and here you can see how this multi-layer fabrication process for electroluminescent display works. So you just spray one layer of copper at first, then you insulate it with dielectric, you spray phosphor under UV light so it's easier to see. So then we need to add a copper bus because these displays are quite large, so we have to make sure that current is distributed evenly everywhere. And then the final layer is the clear conductor. And then you have all components sprayed on top of each other the way it should be. And then the result of this is, as you can see it right here, an electroluminescent display that you can turn on and turn off, and it can also sense touch. So in our technical evaluation, we were, of course, very much interested in the question, like, if you want to integrate this into our environment, like does it actually work on like all these materials? So this combination of materials might look a little bit odd, but we were just like really curious if we can actually spray it on everything. So we also like have an organic sponge, for example, on it. And super exciting was also like the porous stone because it has a really challenging and rough surface. The result of like these tests is that we actually achieved a very, very high conductivity also on like very changing surface materials like the porous stone. So and I want to also like say why this is the case, and we see this here in a magnified example. So in contrast to other print methods, so for example screen printing, which is also very famous for like applying conductive materials, spraying is a contactless fabrication technology. So this means the printing tool doesn't have to be in contact with the material, but it rather has like a beam of particles that it just like presses into the material. And this is the reason why it works so well also like on extremely rough surfaces, because you can put these conductive materials also like in deep cavities and in very rough and uneven surfaces.
Yeah. Okay, I'll be right back.
Okay, so you hear sound, I guess? So here we implemented a music interface. I'm very proud of this particular example because I just started as a postdoc in Stephanie's group, and one of the first things I did was like spraying on the CSAR building, and I didn't get fired, which was amazing thing and very good. So, all right, so what's next? So like things that I'm excited about and in the next steps of this research are like scaling it up. So what we did so far is mainly focused on like furniture size objects or maybe like the walls of an entire room, but it doesn't really scale up at the moment to the surface of an entire building, even like a large building like the one that you see right here. And I'm really excited to also like look into like methods with like robots to have a fully automated process for spraying that even like enables like interactive architecture and creating like smart cities. Yeah. Okay, and the last couple of minutes, because I see like we are coming to an end. So I will just describe the last project about sensing material properties very, very briefly. And so the idea here is the question, can we sense material properties? And the goal of this project was the question, is it possible for a material to be shape aware? So to be able to like sense its own shape and create a digital model of itself while it changes the shape. All right. So as you see here in this video, like how we made this, how we implemented this. So we have like here this material that I cut with a knife, and while I'm cutting it, it can create a digital model of itself with our plugin that we programmed in Blender. So yeah, this is extremely relevant because modeling in the physical world and modeling in the digital world has like both like very big advantages and also like some disadvantages. In the physical world, that we have like these traditional crafting practices, like get haptic feel of the material, we have a stereoscopic view. And the digital world doesn't have this yet, but it has other very, very strong arguments for it. For example, high precision, speed, and like digital tools that can do things that wouldn't be possible in the physical world, right? So, and this is how these shape-aware sensors are built. We have like a set of line sensors, and these line sensors, when they are being cut, they can detect like where they were cut, and stream this information to a digital model, and then create a model out of itself. And you can see this right here. So while I'm cutting it, this change in its shape is directly streamed to a digital model. Okay, and with this, I want to wrap up my talk and then jump a little bit forward. So what we've seen today is a lot of stuff from different research areas that requires like some engineering, smart materials, fabrication technologies, and computational tools. And there's like a lot of stuff that I couldn't show you. So for example, one of my PhD students that I co-advised with Stephanie implemented like morph sensors, so something to distribute conductive traces on the surface of objects and include electronic components. Another project is about controlling material properties, in this particular case, the reflectance of a material. And this project requires a special honorable mention, because I had the pleasure and the great honor to do this project together with the gentleman who's hosting this session today. So, and there's like a lot of like future work. So like extremely exciting is, can we like use printed electronics to produce like more meaningful electronic elements, like printing batteries, for example, and integrating them into like a 3D fabrication process. Sensing and controlling material properties, where I'm excited about going, like finding new ways to create like haptic textures and haptic surfaces that can like change friction, vibration, and heat transfer of material to simulate with one material many other materials. As I described with, as you've seen, like with the sprayable user interfaces, I'm also like extremely excited about like scaling up the fabrication of user interfaces and really like have no restriction about size and materials anymore. And like what is of course a big challenge, like the more we like follow this road, is the more functionality we have, the more complex these objects will become. So what we will need in the future, and this is we cannot avoid this, is intelligent tools that can abstract away like expert knowledge and enable everyone to focus on the design and the functions of the object and less on technical details and engineering. So with this, I want to like finally thank everyone who worked with me over the last couple of years, all this great institution that were willing to host me and let me work there for a while. And with this, thank you very much. Thanks for being here for this talk, and I'm happy to answer questions if we have some time.
Thank you very much for your talk. And we have a little bit of time for a question and answer session. And the first question is for Jennifer. In your talk, you have brought up a very interesting issue of making crafting accessible. And I believe that this is a bit of an underexplored question, especially in the context of fabrication and computational fabrication, where we are attempting to make our algorithms more automated, but we are not really considering the accessibility of them. So do you think there is some way we can improve upon this, maybe some sort of guidelines or best practices that we can do during developing of the algorithms to make them more accessible at the end?
That's a great question. And you know, I think that accessibility is a very diverse set of considerations, so there's not one answer to it. But something that I think we have a tendency to do is to represent things visually. And so thinking about APIs or programmatic access to algorithm content and controls is something to consider in that context. So yeah, I think that's an important thing at the algorithmic level to consider.
Mm-hmm. And then I have a question for Michael. In the project with reprogrammable coloring, is the material that you are using now resistant to the sunlight, or can you just have it outside and will it keep its color, or will the color fade eventually? And do you have any ideas if the color fades, how to make it more stable? For example, in the printer example you have mentioned, where you would make the print afterwards to keep the color once it's printed out.
Okay, this was a very detailed question, but also a very exciting question. So yes, so like this is at the moment one of these opportunities that we have with this material to improve it. So yes, it's true. So like the desaturation happens with visible light. And of course, if you go outside where we have a lot of this visible light, desaturation will happen. And so how we usually pitch this project is that we have like something like daily updates. So like it stays there for like roughly 1 day, depending on which, like how bright the environment is. But you can like reprogram it like all the time. So this is the way how it is at the moment. But what you are working on at the moment is also, if you remember, like we have this like integration into textiles where we're not where we do not rely on an external projector anymore, like an external light source, but we have internal light sources. And once we have achieved this, we can actually like reprogram or like resaturate the material like all the time again. Potentially also like maybe with a photo sensor that just like measures the brightness in the environment and then like knows by how much it should like resaturate the material. And then in the end, like this would be like a very big step forward in making these colors more permanent for as long as you like, and like reprogram it like if you want to change it, right?
Okay, thank you very much for the inspiring talks. And I would like to invite you and the audience to the post-talk discussion where we will be able to ask more detailed questions afterwards. So thank you very much.
Thank you very much, Michal, and great session sharing.
Yeah, thank you.
Thank you. Bye-bye.
Bye-bye.
Bye.